Swayam Prabha. Digital India. Educated India.
Right on schedule today. I had deferred working some further examples with columns last week, and so we're basically going to combine that with the working some examples with beams, and then we'll work that from there into looking at general method, how that compares to doing more of a traditional calculation. So that's our day 7. Then the tutorial session 6, all this kind of flows together, but we're aiming to also get started on lecture 21, and Balint's going to basically look to walk you hands-on through the creation of the model for this gabled frame that you see on the screen here. The aim is to work through the fairly complete design verification on this frame. It doesn't quite work, and then we want to increase the wind load and ask you to try to use consteel to get it to work, and figure out, okay, how can we do this at least cost? Can we take some weight out of the frame or some cost out of the frame, and also at the same time meet the higher load demands and take care of where this frame doesn't quite work at present. Okay, so that'll be kind of more of a working session where my idea is for you to get together in groups of 4 to 5. Pretty much try to talk through, okay, how do we approach this, and let's have some fun with it. By working using consteel for the calculations, we've got the full support here, right in front of us, and to address any questions that are coming up. I think it should be useful in terms of pulling a lot of the concepts together that we've been looking at. Okay, so this is a clear span gabled portal frame that is actually an original design that shows up in the Metal Buildings book that was written by Lee, Ketter, and Su in 1981. Okay, and so the loads that I picked for this are reasonably close to the loads they had. I'll show you some information about the loads shortly. The loads are ASC 7 loads, so obviously it's not the Indian loads, not the Eurocode loads. I put the frame near my hometown, which is in pretty much coastal North Carolina, so we got some pretty good hurricanes there. So the wind load is decent, but you can go to places that are more severe. Other than that, it's a fairly representative design, and Balint will walk you through the details of creating the model and all the important attributes of modeling this frame in consteel in his discussion later today. What I want to do in the first part here is, I think it always helps, rather than to say, oh God, I got this big frame that has a whole lot of load combinations, how am I going to make sense out of all this? So I basically have taken the governing axial load and moment from the design, the analysis design that we're going to talk about later, and let's isolate the column. We pretty much make a cut right at the bottom of the panel zone, and we'll we'll idealize the boundary conditions just as torsionally and flexually simply supported. So that misses continuity effects that Balint's going to talk about that we can capture when we do the model in terms of the 3D behavior, restraint of lateral bending, restraint of warping, and how that works through the knee joint here in the frame. So we're just going to make a release of warping, release of lateral bending in the out of plane direction, and look at what we get in terms of checking the column that way. So that allows us to just focus on the essentials of some of the resistance calculations we've been working on. So I think I touched on all the points here. Some of the points here on this page, Balint will get into in more detail. We're basically modeling one member for the column, and we're splitting the roof girder on each side of the ridge into two members for the calculation. And he'll talk about what are the decision points in setting that up and doing it. The governing loads from the LRFD, ASCE 7 LRFD load combinations I ran are PU of 153 kilonewtons and MU 403 kilonewton meters. So these are the loadings. Obviously, as an engineer, when you need to check a frame like this, if you want to analyze every load combination that the load standard throws at you, you've got a lot of work, right? And so what do? You say, okay, what do I expect to potentially be the load combinations that are going to be the most demanding on the frame here? So we're basically going to be looking at a combination of dead, that's upper left here, roof live load. You can see I've got the loads both in kilonewton meters as well as, for my own benefit, kips per linear foot. Balint and I were discussing what is a kip earlier today. We usually just draw a picture of a little guy and say this is Kip, and we're going to put him over here. This is in North Carolina. Yeah, we have a little bit of snow in North Carolina, but the snow load isn't huge. The roof live load, I think is the more damming load here. And then the wind loading. So basically, the wind loads that I calculated from ASCE 7 with a negative and a positive internal pressure. And so if we take these, I guess I had one load combination jump to the next page here. So we're going to do by ASCE 7 load combinations, a common, pretty much your maximum point in time live is the first load combination. So that's 1.2 dead plus 1.6 live in ASCE 7. Then the next combination is that with wind with a negative internal pressure. And that's going to end up giving us a lot of the most largest demands in portions of the frame, but we'll be able to look at envelopes of what we're getting from these load combinations later once Balint has us there, and we'll see that different portions of these members are governed by different load combinations. The third load combination that I included is 1.2 dead plus 0.5 live and then plus 1.0 wind. Now, if you're not familiar with ASCE 7 wind, it's basically 700 plus year recurrence interval that's used with a factor of 1.0 in the current ASCE 7. And so that's pretty much, that's our design event that for strength that we're working with a load factor of 1.0 for wind. And then the fourth load combination is more of an uplift load combination, 0.9 dead plus 1.0 wind with a positive internal pressure. And of course, these wind loads can act left to right or right to left, and we'll address that by basically ensuring that we have symmetry in our design, of the frame. So Belin's going to pick up with this, and we'll probably get at least a part way with developing the model of this frame today, later on. And again, the frame is reasonably close to satisfying strength design requirements, but it doesn't quite work. It worked in George Lee's book, but I changed the wind loads a little bit to make them more current. And then where are we going? The thought here. So we'll see how well this goes. I consulted with Belint about okay, should we give you guys an easy assignment, or give you something that's challenging? And of course, Belint just ran across the highway and through all the traffic the other night to get to the city of Chennai. So he's an adventurous guy, and he thinks that you guys should be adventurous also and really try something challenging for this frame. So we'll see how it goes. The suggestion, well, I guess it's coming up on the next page. At the risk of being completely silly, I think I got the cost so they made sort of sense the best I could by my use of Google. But please correct me if it's like, wow, boy, I would never sell a frame that cheap, or what the heck is going on here. I think I got the cost as representative, at least according to Google, and didn't mess it up. So we'll say that the cost of the fabricated steel is 700,000 rupees per metric ton, and so one thing to think about, I guess I'm kind of tipping my hand here. One aspect in terms of the cost, and you remember I mentioned that with these frames, metal building manufacturers will typically, or many of them, will do a design of the frame first, where every purlin and every girt location is assumed to be a brace point, unless you know there's going to be a door or whatever where you can't get bracing somewhere. So, and then they come back. In the States, it's often called a bracing reduction stage of the design, where they consider, okay, so now we've got a frame design. What braces can we pull out, and we really don't change the design. That's one way it's done. I've been told by some engineers that are involved with development work for some of the different firms that maybe that doesn't necessarily produce the most economical frame. It definitely gives you a frame that's very light, but you may need to brace it quite heavily. So we have, if we look back at the sketch here, where you see the lines here, there's a number of lines coming off of girts or purlins. So those are all flange diagonals spanning from the girt or purlin and then framing in close to the inside flange to brace the inside flange. We're not going to design those braces along with doing this frame. Belint may talk about some of that with his latter lectures looking at stability bracing with metal buildings. But the idea is there's a kind of a silly cost associated with each of those diagonals, and so you can add diagonals, but there's a cost associated with that, and so you need to weigh, okay, is it more effective to add a diagonal and gain some benefits from that? Do I gain much of a benefit, etc.? But there's many other aspects, I think, for us to talk through in terms of, okay, how well is this frame working? How can we make a more efficient design than this? So the guidelines, we'll kind of come back to these later once we've kind of worked through the modeling, analysis, and design verification with Belint on the frame that you see here. Once you're getting into your groups, okay, let's kind of start by contemplating and discussing what are the various ways you can make this frame design more cost efficient. And then we'll use Consteel entirely for the verifications. And so that, that eliminates the drudgery of, even if you've got MathCAD Prime worksheets, it's still a fair amount of work to go out and start doing all the various calculations on your own. So we'll use Consteel to pretty much drive things and try to have some fun with it and see what we can do in terms of making the frame more economical while still addressing more load. And I guess last thing, and then we can talk more about it later, I would suggest maybe trying to size your column first. That was my first thought was, okay, maybe we just ask you guys to size the column. And then Blunt said, nah, that's too easy. We need to do the roof girder too. So we'll look at how can we work on the whole frame here. All right. So with that said, let me show you. I want to start by basically, so these models are all there under the, I guess the analysis files for module. This is still module 4 or module 3. I think I added a number to some here. Module 3, beam behavior and design. And we'll transition from this into some things where we're looking at the next module. And so, just to get started, boy, the base of that frame sure looks awfully wide. How do we make that a simply supported base? Not very easily, huh? But we're going to say that's a perfectly pinned base, and we've got the supports. But instead of it being tapered, we're basically saying, okay, let's first suppose that we had this member and we want to check its axial compressive resistance, and we're going to use the cross section that's defined in the frame at the bottom of the knee. Okay, and so that cross section is the total depth is 1,000 millimeters. The web is 5 millimeters thick, so it means you have an it's doubly symmetric, so you've got an H over TW of 200. That's you can go a little bit thinner than that before you hit section F13 of the ISC specification that will basically put a limit on, okay, you can only go so thin before the specification doesn't allow it. So you can go to about 220, 230 or so with grade 50 steel, I believe, if I'm going from memory here. We can look at that equation later before the specification would not allow it. So fairly thin web. And then we also have flanges that are 150 millimeters wide and 6 millimeters thick. And so the flanges have then a B over 2T of 12.5. And this is pretty darn close to the design in George Lee's book. And then Belinda and I were looking at this a little bit over the last few days, preparing for sharing this with you. And we said, boy, that's about as extreme as you get in terms of combined thinness of the web and small, relatively small, thin flanges. Okay. So, all right, we're working kind of on an extreme here, but so some of the characteristics will probably be more exaggerated, you might say, compared to what you may see in your final design. Okay, I'm going to tip my hand and suggest some things for you to do in your final design. I don't want to do that. So that's the problem here. So we're just looking at how does that, what sort of resistance do we have for this if it's prismatic under a concentric axial compression. We can do our analysis, and if I go to the buckling, nothing super fancy here. The way this is braced, if we look at it from the end, see if that's the right end, yes. So yeah, so it's buckling out of plane in a braced buckling mode, and we're basically restraining displacement at the girt location from the girt and the flange diagonal to the inside flange. So that's how it's failing under concentric axial compression. You can see that our elastic buckling eigenvalue is 11.97 here. And then we could pull well, obviously this is just applying concentric axial load to this, so it's clear what the demand is in terms of the axial force. So if we come back to this, what I want to do is to basically step through some checks, and let's see if I can maybe make that a little bit bigger. All right, if your eyes are better than mine, you may be able to see that on the TV now. Or you can either follow along. This is, so I've got basically multiple PDF files we're going to step through and look at, okay, how do these design calculations work? So obviously I threw this at you last week, and then of course the professor always expects he just says something in about 5 seconds and you've got it and you're ready to run go use it, right? So let's kind of step through it and hopefully we can get things to gel a bit with how these calculations are working. So this is focused on what we spent time with last week, and how do the column axial compressive strength calculations work in the AISC 360 specification. We'll kind of try to work in, okay, what are differences with how the Eurocode is working again, i.e. then Indian code very similar to Eurocode as we're moving along. So you're using grade 345 steel here. A lot of metal buildings manufacturers metal buildings in the U.S. I'm not sure if it's common practice here or not, but the U.S. they'd often use this is what we call grade 50 steel, 50 KSI yield in the U.S. and it's very common to use a grade 55 steel in the U.S. Would that be common also in India? Yes? 50? Okay. Yeah, I think in many aspects it's really the same steel, but they grade it for a 10% higher yield strength and
350, but now
okay.
using 350 now.
All right, thank you. Okay. So again, you can see the axial load that we're checking, PU, AISC notation is 153 kilonewtons. So I'm calculating gross area. That's just the sum of the areas of the 3 plates. Weak axis moment of inertia. So then we talked about non-slender plate limits. And so if I say I have a slender flange or a slender web in axial compression in AISC, what does that mean to you? Did you get that takeaway from last week yet? Crickets. Okay. Slender web or a slender flange, what does that tell you in terms of characteristics of the plate?
Width should be reduced effectively.
The width should be reduced. If you want to make it more efficient, possibly, yes. Anybody else? Okay, good. Yeah, if it's non-slender, it means we can get it can be a stub column, and we can take it all the way up to yield, and we don't really have to worry about any reduction in strength from local buckling. If it's slender, it means that okay, we're not going to be able to do that. Now, the way the AISC provisions work, per Dr. Taman Pecos's work, Dr. Kalyan Ryman was basically involved with him in a lot of that work, early work at Cornell. And so the so-called unified effective width in the American provisions, we look at calculating a column stress at strength based on gross section properties. So we talked about the logic behind that last week, that And Dr. Pecos basically observed in his research that, yeah, he could say, oh, I need to get an effective moment of inertia and an effective area, and then I get a radius of gyration, square root of I over E. And he said, gosh, I'm getting about the same radius of gyration as the gross, so why don't I just use my gross section properties to get my column stress, okay? So that's the approach, right or wrong. You can say all these approaches are either right or they're all wrong. There's nothing. It's not science, right? It's engineering. You can have a slender element, but if the column is really long, the stress may be so low in terms of your column stress at failure. We use that to calculate the effective width. And so you may have, the section may be fully effective because the stress is low at failure of the column. Okay? Now, Eurocode takes a different approach than that. In the Eurocode, we say, okay, I want to check my effective widths of my class 4 plate at yield. So I get an effective widths based on yield. Then we have a cross-section resistance. Once we have a cross-section resistance, then we have a chi factor that reduces the cross-section strength based on whatever column curve is appropriate for the section we're looking at, right? So there are a lot of similarities to both standards, but some very different ways they work. I think I captured reasonably kind of what is happening with each of those standards here. So these lines here in the middle of the page now, table B41A and section E7 is where we do the column capacity calculation, or that's the provisions for that. Our web H over TW is 198. So H is the distance between the insides of the flanges here. And that clearly that's much larger than the non-slender web limit, 1.49 square root over Fy, which is 35.9. So we're plenty slender here for the web. If we look at the flanges, we use half of the flange width over the thickness as the width to thickness ratio in the US practice here. And for a thin web, I'm not showing you the equation, but the equation is Kc is 4 over square root of H over Tw. And 4 divided by square root of H over Tw. And you calculate that if you get a number smaller than 0.35, this is basically a plate local buckling coefficient. That's a hip shot local buckling coefficient to do the calculations. And if you're less than 0.35, you limit it at 0.35. You don't go less than 0.35. So for anything that's a plate that has an H over TW larger than 131, if you plug it in, you're going to be at 0.35. Anything with an H over TW less than 131, then the stockier the plate, K sub C of the web increases. So that's representing here what sort of restraint or destabilizing effect can you get on the flange from your web. Okay. Does anybody know what the plate local buckling coefficient should be for a flange element that we assume is simply supported at the web and then has a free edge? I didn't think you would. Or some of you, what is it? Yeah. Hey, all right. You guys are on your toes. 0.43 or 0.425. Okay. All right. So 0.35. That means the web is so thin it's actually destabilizing the flange. Okay. So we plug that into that. That's part of the equation for the non-slender limit of the flange here. when we have a welded 3-plate section, we got lambda RF is 9.12. Okay? So we got slender web and slender flanges in this cross section. Lots of fun. So I showed you, we did the buckling analysis. In Consteel, we got 11.97. We're kind of throwing around notation a little bit here. So using the preferred American term, we've got a gamma, and I've told you a couple of times now that in the AISC spec, we're trying to move in the direction of anything that's an elastic buckling quantity, a subscript CR. But we're not quite there yet. We've got subscript CR on some things where it's talking about other stuff, and we use a subscript E on some things for elastic buckling. So lots of things to confuse you in terms of notation. But I'm going to call it gamma critical, and then .op here for out of plane. Okay, we had a flexural buckling out of plane. All right, how are we doing so far? Pretty good? Okay, all right, so now let's take this eigenvalue we're getting from Consteel. That's the multiple of the design load that we're applying that gets us to theoretical elastic buckling, right? So we don't need any silly effective length factor. We've got Consteel. We run the buckling analysis. We've got a buckling load. Okay, well, we can back calculate an effective length factor just to kind of understand where we are with things. So that's what I'm going to do next here. Or in terms of stress, the elastic stress on the gross cross section at theoretical elastic buckling is 272 megapascals. Okay? All right, so now just to get a feel for where we are, so remember we've got two unbraced lengths in this column. The bottom unbraced length is 2.2 meters, the top unbraced length is 1.5 meters. And if we go back and look at our model in Consteel, you can see that the bottom here for this loading is kind of tending, you can see it's a little more deflection in the buckled mode there. The top is kind of tending to restrain the buckling of the bottom, similar to one of the examples that Balint was showing or walking us through yesterday, right? So if we take this load, 1831, and if we equate that to pi squared EI divided by KL squared, solve for K, so that's essentially what I'm doing here on these next two lines. I can see that my bottom unbraced length has an effective length factor of 0.87. Less than 1. Why less than 1? More fixed. Yeah, okay, why is the top one greater than 1? Okay, so the bottom segment is so the top segment is less apt to buckle than the bottom because it's not as long, right? And so the top segment is tending to restrain the bottom segment, but they both go together when it buckles, right? And so they're both buckling at the same load, the 1831 kilonewtons. The bottom is tending to destabilize the top. The top is tending to help stabilize the bottom. So the bottom is buckling at a load a little bit higher than just the pin-pin load because of the restraint from the top. The top is buckling at a load a little bit smaller than the load for a pin-pin column. That all good? Okay. So from here, we're going to calculate a column non-dimensional slenderness. Again, and if you see me in a month or two and I'm all black and blue, it's because they got me in a corner at the AISC task committee meetings and beat me up and told me no way are we going to use a lambda in the AISC specification. It's damn the torpedoes. We're moving ahead, and we've got a lambda that's been approved for at least lateral torsional buckling in ballot 2, with a couple of significant prominent dissenters, but then like about 48 votes yes. So have to argue a bit at the next task committee meetings about lambda. Okay, let's talk about it. So if we look at what we've got here, so if we, here's the buckling mode. If we go back to the bracing, so it's the same cross section, top and bottom segments, but the bottom is 2.2 meters long. The top is 1.5 meters long, right? So the top would be stronger, correct? All right, but they buckle at the same axial compression together. Okay, so now we're going to get a non-dimensionalized slenderness. So AISC 360, back when it was AISC LRFD spec, LRFD alone, the column strength formula had, guess what? Lambda. The exponent, it had an exponential equation to the lambda squared and had an elastic buckling equation that involved lambda. And the area specification committee is very driven by interests of the steel industry to promote design and interest of designers to do design. And these pin-headed professors that want to introduce a lambda, well, you guys can go sit in the back row. So I think when we were moving from to the unified ASD LRFD specification, the suggestion was, we don't like lambda, we'll just call it FY over FE. Okay, so we're trying to, there's many reasons that we've already talked about, and we can talk about some more why it's good to put it in terms of a non-dimensional slenderness for our stability design. So we're getting a 1.13 here for the square root of yield load to elastic buckling load, or yield stress to elastic buckling stress, or we can write it as, if we call this a design to capacity ratio, DCR, so we've got our design, demand to capacity ratio. PU is our demand, right? It's our loading demand. Capacity in terms of gross cross section, well, that's yield load, PY, FY times AG. So that's what we're doing here in working with a gross cross section when we're working on our column, to get our column capacity. Okay? Now, again, remember I mentioned a big point I tried to make later last week was in the column strength checks, particularly when we go to non-prismatic columns, we need a gamma E, or a gamma critical is now what I'm calling it. That's your elastic buckling eigenvalue. And we need a, essentially, okay, what's the cross-section demand to capacity expressed in some way. Once you've got those two, you've got everything you need to be able to calculate the PU over phi PN, your member design demand to capacity ratio. And you don't necessarily, you can use a K-factor to get your elastic buckling load, but you don't have to use a K-factor. If you've done a buckling analysis, you've got your buckling load, right? Okay, so we've got a non-dimensional slenderness for the column. Now we go to our column curve. It turns out that this non-dimensional slenderness falls in the range that would classify as inelastic buckling. And so this is the exponential equation that gives the inelastic part of the AISC column curve. And we go, well, okay, this we've mapped from an elastic buckling resistance now to a resistance considering imperfections, considering inelasticity. So at a stress of 203 megapascals, we expect the column's going to give up. All right, okay. So that's the way we're doing it in AISC. Everything's gross cross section at this point. We've got now an FN. Now we're going to use Dr. Pecos's unified effective width approach concept, and we're going to say, okay, I give an FN, let me calculate the effective widths of the plates. So we come back to our web. Again, the H over TW of the web was 198. Now, this inequality that we're checking here, if Fn is small enough, the quantity on the right could be larger than 198, but that's going to be hard to do for such a large slenderness. So that goes up to 46.8, but we still have, this is still telling us we've got to take an effective width reduction to get our column capacity, right? All right, so here's the equations in AISC again for getting the column strength. We've got the coefficient, we use 0.18 for the web here instead of 0.22, which is kind of the standard Winters equation. C2 of the web that goes along with that is 1.31. We spent some time glazing your eyes over and looking at how we dive in and do a deep derivation of C2 given C1 late last week. And so here's Dr. Schaefer's equation that basically says, okay, given a non-slender limit, lambda RW, given your plate slenderness, lambda W, let's calculate the elastic buckling stress. It's just another way of calculating another equation for the elastic buckling stress. It's equivalent to the one that you're probably more familiar with from mechanics. So it's going to buckle at a stress, theoretically, of the web would snap into a bent plate bending mode, local buckling mode at 19.52 megapascals, fairly low stress. So now we can take that elastic buckling stress, our Fn instead of Fy, and we can calculate the effective width of the web. So we got 289. You can see that's only 29.3% of the total width of the web. So we have quite a substantial loss of effectiveness of this web due to local buckling. The effective width is letting us calculate a post-buckling strength for the web. We need to do the same thing for the flanges. The flanges are almost to where they're fully effective for the Fn that we've calculated for our column. 12.5 versus 11.9, but we're still going to have to take some reduction in the flanges. So the flange equation uses Winters' coefficient of 0.22. Same equation here to get an elastic buckling stress of the flange, theoretical elastic buckling stress when the flange would bend out of plane in local buckling, 407 megapascals. We bring that into our flange effective width equation, 146. And you see it's just a minor reduction here in terms of the effectiveness of the flanges. So now we just add them all up. We get the total cross-section effective area. And you can see that this section is about as extreme as any I've ever seen. It's like, it kind of surprised me, but it was the original. It's very close to the original design that was in the book by Lee, Ketter, and Sue. So it's representative. You can certainly get these sorts of dimensions in a metal building frame. But effective width is less than half of the gross, effective area is less than half of the gross area. So now, unified effective width approach, we simply multiply Fn by effective area, hit it with the resistance factor, so our strength is 584, and so our design to capacity ratio, Pu over Vpn, is 0.262. Okay? So any questions there? I wanted to step through that one very carefully. I want to go faster through the next where it's kind of where we kind of rinse and repeat with a non-prismatic section.